Welcome everyone to EPA's monthly webinar series for small drinking water systems. This is a collaboration between EPA's Office of Research and Development and EPA's Office of Water. Today's topic is source water protection. If you're interested in downloading the slides for the talks today, you can find them in the handout box located in the navigation panel on the right side of your screen. Before we start, towards the bottom of this slide is the webinar support phone number, so if you're having webinar problems, please use that. The recordings of this webinar and past webinars can be found on the website at the very bottom of this slide. Also, we will be having an optional Q&A session after the conclusion of both presentations. If you have questions for the speakers, please type them in the question box at any point during the presentations, and we will try to answer as many questions as possible. We are offering a certificate for one continuing education contact hour for viewing this webinar, which I'm going to discuss on the next slide. So these are the requirements for receiving that CEU. You must be registered for the live webinar or be in a room with someone who is registered. You must attend for 60 minutes, and if in a room with others, the names of the people not logged in must be provided by the person who is logged in, and you can send those names to webcastinfo@cadmusgroup.com. If you did not request the credit at the registration, send an email request to, again, webcastinfo@cadmusgroup.com or respond to your registration confirmation email. Again, if you missed the poll question and have more than one person in your room, please type that number into the question box. This helps us document attendance, which in turn helps us justify this webinar series. So also, if you have any stories on how the webinar has helped your agency or organization, you can type those in the question box as well. We'd really appreciate hearing from you. So I'm going to go ahead and introduce our first speaker, who's going to be Bo Williams. Bo is a biologist in the Drinking Water Protection Division of EPA's Office of Groundwater and Drinking Water. And as a member of the Source Water Protection Program, he manages geospatial analysis and outreach in a variety of projects to protect sources of drinking water and supports the National Source Water Collaborative. I'm going to go ahead and pass it over to Bo.
Thanks, Victoria. As she said, I'm Bo Williams. I'm with the EPA's Office of Groundwater and Drinking Water, and I'm on the Source Water Protection team here at EPA headquarters in DC. Today I will discuss a few online mapping, data exploration and sharing and outreach tools that are publicly available. That means free, and they can be used by small water systems and others to inform their source water protection efforts and hopefully, ultimately, help them deliver clean drinking water to their customers. I'm excited to have the opportunity to present on this topic today because I think there are a number of new, accessible, and very cool tools out there that are making our job easier and more effective. And I think you'll be excited to see what I'm talking about. Specifically, I will discuss and demonstrate a few tools developed and available on ESRI's online cloud-based GIS platform. ESRI, which stands for Environmental System Research Institute. I worked with their products a bunch, and I actually never knew what the acronym stood for until earlier today. But ESRI is the maker of the ArcGIS program. Primarily of those tools will be DWMAPS 2.0, and that stands for the Drinking Water Mapping Application to Protect Source Water. And that's EPA's updated mapping tool that's now based on the ESRI platform. For the purposes of today's demo, I'll demonstrate how DWMAPS and the other ESRI tools can be applied for source water protection. And I'll use a hypothetical example from Mount Vernon, Ohio, which is a small town in central Ohio, and also where I went to college. So using the Mount Vernon example, I'll show you how these tools can be applied to support source water assessments and wellhead protection plans, and how these tools can help you to make them a less onerous and more continuous and adaptive process. How you can use these tools to identify and characterize potential sources of contamination so you're prepared for a spill or emergency situation. how you can use these tools to view and manage water quality monitoring data. With these, you can view monitoring data from various sources, whether federal, state sources, or local, alongside your own that you've uploaded. I'll also show you how these tools can help you develop a comprehensive picture of source water threats, so you can begin to prioritize protection strategies and a protection plan. Leveraging authorities provided by the Clean Water Act and other environmental programs to protect source water can be an important strategy. So in DWMAPS, we've gathered information from across environmental programs to help you visualize where in your watershed you can engage. However, as you know, developing strategies doesn't necessarily get you far if you don't have buy-in and support, financial or otherwise, from watershed or aquifer stakeholders and those of influence to put your plan into action. There are several excellent new tools that can help you present your findings in a format that is visually and conceptually available that can help with your whole partnership building effort, and those are provided through Esri as well. So before jumping into the Mount Vernon example, let me first tell you a little bit about DWMAPS and Esri's online GIS platform, at the risk of sounding like an Esri sales pitch, upon which DWMAPS is based. So what is DWMAPS? DWMAPS is nominally an online mapping program for viewing and accessing data critical to drinking water source protection. Similar to other online mapping tools, such as EnviroAtlas, that's an EPA tool, and a number of state-level tools, such as Ohio's, which I'll show you later. DWMAPS allows users to layer data spatially to make visual connections. DWMAPS draws from several databases, federal databases, a few of which I have here in the honeycomb graphic. Of note are Waters and Attains, which house Clean Water Act specific information, the Facility Registry Service, which houses information on EPA permitted facilities. We also have information from USGS and from the Safe Drinking Water Information System, among others. There are many more, and there are many more that you can access. DWMAPS itself also provides several query functions or widgets that help users sift through the various available data layers. It also serves as a data portal or clearinghouse through which users can find and access source water protection related data for their own maps and analyses. And it's in this area that the DWMAPS 2.0 capabilities. So DWMAPS 2.0 is our new version this year, but it's in this area that DWMAPS 2.0's capabilities and opportunities for users have greatly expanded by moving to Esri's online GIS platform. Now, anyone with an ArcGIS online profile, again, profiles are free. Not all the products for Esri are free, but all the ones I'll show you today are in fact free. So anyone with an ArcGIS online profile can draw data sets found within DWMAPS into their own managed maps. They can view them alongside their own data or alongside any content shared by Esri in the GIS user community around the world, including from states, local governments. Your dog can put something up there, anyone. You can also share your own products, such as data layers, maps, and applications that you've created with anyone you please. I think these capabilities make the new version of DWMAPS a much more adaptable and customizable tool than the previous version, and we'll continue to work here at EPA to develop and enrich data sets that we think may hold value to our users. So for the purposes of today's presentation, I want to show you how you can apply these tools using Mount Vernon, Ohio as a case example. Mount Vernon, as I said, is in central Ohio. It's located in Knox County, the county seat there. It's about 60 miles north of Columbus. The City of Mount Vernon Public Water system is the primary provider for the area and for that town. They draw all of their water from 2 pumping wells at about 3.5 million gallons per day. They serve greater than 17,000 people, which I realize is not a small system, but is close and is a compelling example to use here. Mount Vernon draws their water from the Kokosing River buried Valley Aquifer, which is pretty shallow at about 15 feet below the surface of the ground. Firstly, these tools, including DWMAPS, can help you update your source water assessments. And the first step of any assessment should be to delineate a zone of concern within which to identify potential contaminant sources. Here I've pulled protection areas or the zone of concern information from Ohio EPA's Source Water Assessment and Protection Program mapping site. Thank you very much, Ohio, for making this available. You can see the interface of Ohio's source mapping program on the bottom left there. And here they provide web services to all their data sets. It's, I believe, also based on the Esri platform. So I simply went into their mapping application and grabbed the services and placed them in DWMAPS. So the image on the right side is actually an image from DWMAPS. So with this, you can, I could use these defined areas to see where I should look for potential source of contamination for Mount Vernon. Ohio EPA first completed their source water assessment for Mount Vernon in 1997. They updated in 2011 when Mount Vernon closed one of their intake wells. They adjusted the protection area at that time to reflect these changes. And if you look at the image there, the kind of lighter blue, bigger area within the map represents what they call a source water protection area. And that represents a 5-year pumping distance, and that's based on 5 years time of travel. The kind of darker blue, smaller area is what they call the inner management zone, and that's a 1-year time of travel we're pumping. And these terms were pulled from their source water assessment, which is available online. So if a source water protection area or wellhead protection zone isn't available from in that format or in a format that's readily placed into your map or within DWMAPS, we've actually provided within DWMAPS a few query tools or widgets that you can use to look for contaminants by a particular area. Firstly, you can search by a buffer radius, and that will highlight contaminant sources 1 to 30 miles around a point that you've selected. You can also view upstream from a point if you're a surface water system. And that will highlight contaminant sources 1 to 10 miles upstream from that point. It's important to note that these 2 queries and all the other queries, you can see the icons on the bottom of the image there represent our widgets or queries. But all these queries are public, meaning that they can be brought into your own ArcGIS online map or added to a mapping application and applied to your own data sets as you see fit. So the next step of any assessment, let's say, is to complete a potential contaminant source inventory. DWMAPS itself provides access to a number of federal contaminant source data sets, including the National Pollutant Discharge Elimination System, or NPDES, the Toxic Release Inventory, or TRI. They also provide information on Superfund sites, oil and gas, brownfields, hazardous materials, railroads, and many more, which you can grab there. And with many of these data sets from DWMAPS, you can drill down deeper to find information on which specific contaminants can be found at that site. And you can also find discharge monitoring reports and compliance reports. The image on the screen shows a facility report from the ECHO database. DWMAPS also has several non-point source pollution layers as well. And they also have a few layers indicating natural or protected areas that may be of interest if you're considering pursuing land conservation or preservation as a potential protection strategy. The image here shows the National Land Cover Database, which shows land use and land cover. The brown or yellow areas generally represent agricultural areas. The green generally represents open space or forested areas, and the red and pink are more developed or commercial areas. I've also uploaded parcel data and zoning data from Ohio's map. And you can use these, you can use parcel data to develop a build-out scenario, which can give you a good idea how a changing landscape may affect your water quality in the future. Or you can use this information to reach out to landowners in important recharge areas. In this image here, I've uploaded point location data that I put together on septic systems. It's completely made up information. I inputted these from a spreadsheet that I created. But as long as you have geographic information like lat long coordinates, I can upload and view data in the map. So I could have uploaded waypoints taken from a field GPS system. I just downloaded this week because I was curious an app on my phone that will take waypoints, and I could have used that information as well and uploaded it to the map here. I think it's important to note that this image is actually taken from another map. It's not taken from the DWMAPS interface. And I simply made this map on my Esri profile. I'd also be able to upload this information on the DWMAPS. However, within your own maps, like this one, you have access to a number of geoprocessing and data visualization tools that are not yet available in DWMAPS. For example, you can adjust symbology or how the information is viewed. You may be able to filter or select information based on particular search criteria, and lots more. And I'll show in future slides other things that you can do on these maps. Of course, you don't have to limit yourself to contaminant source data. I could also upload water quality monitoring information and maintain maps with data points gathered over time. You could, for example, develop a time series map with these free products and show the magnitude of changes over time. In this image, I've developed a heat map from monitoring data that I inputted. The yellow areas show areas with higher contaminant values. That's just to give you kind of a quick idea of one thing that you can do in your own maps. There are a multitude of options open and available to you to manipulate the information and how it's presented. Also, a thing I should note, Esri has developed a real-time GIS tools that display streaming sensor data that can be used to establish spill monitoring and downstream emergency notification systems. I personally don't have experience with these tools, and you may have to subscribe to get access to a number of those, but they may be worth checking out in your own time. So here are the results of my sort of rapid source water assessment. I've identified several different potential contaminant sources, including a few auto repair shops, a few gas stations, some oil and gas sites, a few locations that have hazardous materials. There are also a number, pretty wide area with crop agriculture. With DWMAPS, I found 7 potential contaminant sources in the inner management zone and 34 in the source water protection area. And that compares to 46 total that were identified in Ohio EPA's source water assessment from 2011. 17 of those were identified within the inner management area. And I found several contaminants that were not represented in their study, and they include a number that we did not see in DWMAPS, including a number of oil and gas sites. And I bring that point up to emphasize really an important point, and that's that DWMAPS and other remote sources of information, whether state, federal, or whatever, are indeed valuable for identifying contaminant sources, but they do not provide the full picture always. DWMAPS cannot be a substitute to local knowledge and information on the watershed. It should be used as a complement. So I'd encourage you to present your findings if you do use DWMAPS and reach out to local organizations, government bodies, emergency personnel, landowners, whomever. They may have monitoring or contaminant location information, land use information, anything that can help you to get a more comprehensive picture. In your sort of outreach and information gathering process, it's not only necessary to get a full picture of contaminant threats, but it's also an important step in conceptualizing and prioritizing strategies to address these concerns, and ultimately for developing the relationships with watershed partners that will help implement your protection plans. In that context, it's very helpful to know what's being done in your area of concern to address pollution, who may be able to help you implement your protection strategies, or where opportunities may exist to engage in regulatory processes to improve protections. You really have to get the full lowdown. DWMAPS itself includes information about Clean Water Act programs, such as the location of NIPD's permitted facilities, impaired waters, TMDL information, and water body assessments, water quality assessments. And these can help you identify opportunities to leverage these programs to protect source water. In this image here, we can see local waterways in Mount Vernon that are impaired for organic matter content. There may be an opportunity here to improve land uses within my protection zone if a TMDL were prioritized for development. So this is just one way to view information on the Clean Water Act that can may provide you with a path forward. DWMAPS also provides information on local source water collaborative groups or local organizations working in the watershed, should you wish to reach out to these organizations. As I mentioned earlier, and as you know, effective source water protection requires the support and cooperation of a variety of watershed partners. So I'd say the outreach process is foremost an opportunity to work towards a kind of shared understanding and hopefully to a shared commitment to action. But communicating or you would even say selling your vision and fostering buy-in can be a really huge challenge. DWMAPS lets you print out maps and download search results into reports. So you could take the information you found in a handy format and maybe present that to a city council, an NRCS technical group, or whomever you would like to reach out to. But Esri has also developed a number of very cool outreach tools to help you engage your audience and help you convey information in a way that is conceptually accessible and I'd say at times inspiring. One tool you may want to use is the story map, which there's an image here of a story map that I developed. Story maps allow you to present maps and data, images, and media together to tell your story. So I'm going to go in quickly and view the story map. Hopefully this works. So as I just said, story maps are one way for you to kind of organize information and put it into a format that can draw in your viewer and be pretty engaging. It allows you to integrate pictures and text. So I have text here from the 2011 Ohio Drinking Water Source Assessment that I just pulled right into here. You can integrate text with media, but more importantly, you can also embed interactive maps. So I find a map like this much more interesting and engaging to look at than a static, kind of hard to read printed map. So I think this is a very compelling way to present your information, engage interest, and raise awareness. They're fun to play with. I can tell you that I do not have a background in website development at all, and was able to, I've made a few story maps and was able to pick it up pretty quickly. Nope. Is that showing? So that's actually the end of my presentation. Thank you so much for listening. I look forward to your questions. I have put a few links here to important resources and a few links to some relevant source water protection modeling tools that you may find interesting. And I'm going to pass it over to Victoria.
All right, great. Thank you, Bo. So before we move on to our next set of speakers, I wanted to put in a quick reminder. If you missed the poll question and have more than one person in your room, please type that number into the question box. This really helps us with justifying the series and provides us with the most accurate attendance numbers. Okay, so our next set of speakers are all from the Office of Research and Development. James Price is a postdoctoral associate whose recent research focuses on valuing challenges in the quality of water resources. Dr. Chris Nietzsche. Chris is a research ecologist who conducts and directs research programs in watershed ecology, working towards better water quality management systems. And Dr. Matt Haberling. And Matt is a research economist whose current research focuses on estimating the economic benefits of improving water quality and using economic incentives for controlling pollution. So I'm going to go ahead and pass it over to Dr. James Price.
Okay, thank you. This presentation will be split between three speakers, myself, Christopher Nietzsche, and Matt Haberling. We'll be talking about ecological and economic modeling for source water protection. The goal of these efforts, these modeling efforts, is to determine if a drinking water treatment plant has any incentive to protect its source water. I'd like to begin with some background information. We define source water protection to be the protection of water quality, quantity, timing of flows, and associated benefits at a water source before it reaches the intake. So given this definition, there are a number of groups that can potentially benefit from source water protection. These include recreationalists, who may benefit from improved recreational opportunities and experiences, homeowners who may benefit from increased housing prices, and drinking water treatment plants who may benefit from lower treatment costs. Our focus today is exclusively on the benefits incurred by drinking water treatment plants from improved water quality. These benefits fall into two broad categories: avoided treatment costs, avoided capital investments, and avoided operation and maintenance expenditures. These benefits have been widely recognized, for instance, in the 1996 amendments to the Safe Drinking Water Act. But despite this recognition, they have rarely been quantified, at least not using observed cost data. This quantification is the primary goal of the research being presented today. For the next few minutes, I will discuss findings from the existing literature regarding how source water quality affects treatment costs. Afterwards, Chris and Matt will then discuss a study where ecological and economic modeling was used to identify this relationship in a single treatment facility, and then they go one step further to estimate the cost of source water protection. By comparing the costs and benefits of source water protection, they're able to determine whether a treatment plant has an incentive to protect its source water. All right, so turning to the literature review, we did a thorough search for studies that estimated a statistical relationship between source water quality and treatment costs. We looked at both the peer-reviewed and grade literature. We also limited our review to studies that used observed cost data, not projected costs. From each of the relevant studies, we extracted elasticities. So now an elasticity is a measure of responsiveness that is commonly used in economics. For our purposes today, we're defining it as the percentage change in treatment cost given a 1% reduction in water quality. So for example, if we are interested in turbidity, an elasticity of 0.13 indicates that treatment costs would decrease by 1.3% if there was a 1% decline in turbidity. Or another example is an elasticity of 0.6 would indicate a 0.6% decrease in treatment costs if turbidity declined by 1%. So why are we interested in elasticities? Well, there's a couple of reasons, but the main one is that they are unitless, which allows us to compare results across studies that use different measures of water quality and different types of treatment costs. So before turning to the results of the literature review, I just quickly want to mention two important caveats. First is that an elasticity is only relevant for small changes in water quality. And second, the elasticities that I'm about to show you represent averages across several studies and many drinking water treatment plants. They may be useful for policy purposes, but are unlikely to be accurate for any particular treatment facility. So in a few moments, Matt and Chris will discuss a study where an elasticity was calculated for one particular treatment plant. So these are for our literature review. So far, we've reviewed 250 studies. Of these, 26 studies have met our criteria. And from these 26 studies, we extracted 83 elasticities. With a few exceptions, the studies look at operation and maintenance expenditures and not capital investments. Our findings are presented in the table on this slide. The first column indicates the parameter used to represent source water quality. These include turbidity, TOC, nutrients, sediment, and various land use categories. The second column indicates the number of elasticities identified for that parameter. And the third column is the average elasticity from those studies. You'll notice that there's less than 83 elasticities reported in the table. That's because for now we've excluded studies that are difficult to categorize or are slight variations of an elasticity that's already included. So looking at the table and looking across the first row, we see that we were able to extract 11 elasticities for turbidity, and that the average is 0.15. This implies that a 1% decrease in source water turbidity reduces operation and maintenance costs by 0.15%. The corresponding elasticities for TOC is 0.34, for nutrients 0.07, and for sediment 0.24. With respect to forested land, we find an elasticity of negative 0.72. So this elasticity is negative since there's a negative relationship between forest cover and treatment costs. It indicates that, on average, a 1% increase in forested land within a watershed reduces treatment costs by 0.72%. All right, then on the table, you can also see corresponding elasticities for developed and agricultural land within a watershed. Notably, the average value for agricultural land is just 0.07, but this finding masks a lot of heterogeneity in the literature, particularly high-impact practices such as related to tillage or fertilizer applications typically have much higher elasticities. So in addition to these findings, our review also revealed several notable gaps in the literature. There's little information on how water quality impacts long-term costs related to capital investment. Likewise, there's little information on how key contaminants such as algae, little information on how elasticities differ across treatment typologies, and no studies exclusively related to groundwater systems or small systems. All right, so before handing things over to Chris, I want to quickly present a framework for modeling source water protection. Ultimately, the goal is to determine if a drinking water treatment plant has any incentive to protect its source water. To do this, we need to quantify three things. First is the link between water quality and treatment costs. As in the literature review, this relationship can be estimated statistically and reported in terms of elasticity. Second is the link between source water quality and watershed loading. Sometimes the variables that drive changes in drinking water treatment costs differ from the watershed loadings. This requires translating the loadings to variables that matter to the variables that matter for the treatment process. An example of this would be translating phosphorus loads in a reservoir to turbidity. Okay, the third link is that between land use change and watershed loading. And so finally, with this information, it's possible to compare the cost of land use change or land use preservation to avoid a treatment cost to determine whether a drinking water treatment plant has an incentive to protect its source water. So with this general framework in mind, Chris and Matt will discuss their study of a watershed and surface water facility in Southwest Ohio.
Okay, thanks, James, and hello, everybody. This is Chris Neach speaking. As Victoria said, I'm an ecologist. I'm going to be talking about the source water protection watershed side of the domain here. In this section of the talk, I'm going to exemplify our ecological modeling research to estimate the cost of nutrient reduction. We have been doing this within the context of nutrient trading feasibility. I don't have time to go into the specifics of trading here, but using the intention of establishing a market for buying and selling nutrient reduction credits has provided a good framework for evaluating costs and the incentives of potential participants. If a market for nutrient trading exists, it would be easier for interested parties to participate in source water protection. Our case study system is the 500-mile squared East Fork of the Little Miami River watershed in southwestern Ohio, seen in this map. The East Fork has been undergoing extensive monitoring for 10 years in both streams and in Harsha Lake that sits in the middle of the watershed, bisecting it into upper and lower portions. We've been focusing on the upper portion, which is primarily agricultural. The lake is the source water of interest. The lake was formed in 1978 by the Corps of Engineers as part of flood control for the Ohio River. Claremont County, Ohio purchases water withdrawal rights to treat as much as 19 million gallons a day of drinking water for around 75,000 residents. Toxic algae have been increasing in the lake since 2000. The lake started exhibiting large harmful algal blooms that now persist almost the entire summer and in large part are due to a nutrient enrichment problem. Our research in this system is constantly evaluated by for practical application by a stakeholder group, and the logos of many of its members are shown on this slide. The group goes by the name of the East Fork Watershed Cooperative, and without the stakeholder group in place and actively participating, we find it would be difficult to ensure practicality of the research. So to begin to understand what it will cost to fix the algae problem in the source water, we start by setting targets for total phosphorus, or TP, and total nitrogen, or TN, in the streams draining to it. The values chosen are supported by sound monitoring science and are 60 parts per billion for the phosphorus and 700 parts per billion for total nitrogen. Next, we turn to models. Models serve two primary purposes here. They help integrate all of the monitoring data so that it can be considered at the system scale. And secondly, they simulate the effectiveness of management practice alternatives. We chose the soil water assessment tool model for use as it is one of the most commonly used watershed models in the world. The pie charts here on the right are model output, showing the relative contribution of different sources to the nutrient load to Harsha Lake. Soybean production accounts for over half of the 1 million kilograms of total nitrogen and 100,000 kilograms of total phosphorus annually loaded to the lake. One of our primary research goals has been to quantify the uncertainty associated with estimating the cost of nutrient reduction. Part of that uncertainty comes from agricultural best management practice, or Ag-BMP, removal efficiencies. We use the SWOT calibration and uncertainty program to capture this. The Upper East Fork SWOT model is somewhat unique in that it simulates lot-level nutrient loads that scale to the watershed level and is validated with extensive monitoring data. We use the SWOT model along with an extensive literature search on the costs of management alternatives to explore the costs of nutrient reduction in the system. Based on our targets, we need a watershed-wide reduction of 85,000 kilograms per year of phosphorus and 800,000 kilograms per year for total nitrogen. In the upper watershed, that can only come from wastewater treatment plant upgrades, agricultural best management practices, and/or septic repairs. We can estimate what the load reduction requirements are for each of the wastewater treatment plants in the upper watershed. There are 9 of them, and collectively 1,768 kilograms of phosphorus and 6,433 kilograms of nitrogen reduction would be needed from these plants. This level of reduction would account for at most 2% of the nutrient reduction needed at the watershed scale. So the bulk of the enrichment problem will have to be solved by agricultural nutrient management, as will be the case in most Midwestern watersheds of this size. But the wastewater treatment plants still would have a nutrient reduction obligation under this approach. And we contend that they should be allowed to purchase nutrient reduction credits. While this would not meet watershed-wide water quality goals, you'll see in a moment it comes at reduced cost compared to a plant upgrade, and it establishes a need for a nutrient trading market, one that the drinking water treatment plant on Harsha Lake may be interested in participating in for source water protection. Also, by establishing a demand for nutrient reduction credits, we provide an additional incentive to farmers to adopt agricultural BMPs. This helps to decrease the risk aversion exhibited by the farmers when it comes to Ag BMP implementation. So now let's have a look at the unit cost differences for nutrient removal among the management options. We considered residue management, cover crops, filter strips, wetlands, grass waterways, reducing fertilizers, and septic system repairs, and all in comparison to wastewater treatment plant upgrades. I don't have time to fully explain the bar graph shown here, but I wanted to include it to give a snapshot of the cost differences that are all in dollars per pound and plotted on a log scale among management alternatives, and to highlight different aspects of the uncertainty associated with these costs. Among alternatives, septic system repair was the most expensive, followed by the wastewater treatment plant upgrades. Agricultural BMPs, for the most part, were a factor of 10 lower than the upgrade costs. The cost of fertilizer reduction and residue management were quite high among the Ag BMPs and would probably not be worth considering. There are two types of uncertainty depicted in this graph, that from the treatment efficiency and that from spatial location. Generally, accounting for these suggests a doubling or tripling of the base cost estimates pending the agricultural best management practice type. Now let's put the unit cost into an annual and whole watershed perspective for total phosphorus. The graph here shows that it would be $5.4 million for the plant upgrades compared to what could be between $27,000 and $246,000 for the same level of nutrient removal if it was accomplished using cover crops and depending on the level of removal efficiency realized. These are the light blue bars in the graph. The 5th, median, and 95th centile categories capture the treatment efficiency uncertainty in using cover crops. I show the results for cover crops here because they are gaining popularity among farmers. And what this uncertainty analysis suggests is that factoring in the removal efficiency means a factor of 9 or so difference in the annual cost projections for the wastewater treatment plants if they were buying credits as cover crop. We recommend taking the 5th centile of the distribution of treatment efficiencies to be conservative and in place of using a trade ratio or margin of safety. So this 246,000 in cover crops would have to be planted over 7,900 acres of existing row crop. And this is given in the white text embedded in the bars of the graph. Turning to the watershed as a whole, the dark blue bars in the graph, using cover crops to meet the total phosphorus load reduction would cost $1.6 to $14 million. However, the costs here assume that there is enough row crop acreage available for cover crop implementation. Looking at the acreages needed highlighted within each bar, we see that cover crops would need to occupy as little as 51% of the existing row crop acreage to as much as 4 times the amount of row crop that actually exists in the watershed. Okay, so we can't fix the TP enrichment problem with one BMP type alone. The graph here shows the total costs and BMP coverages needed to achieve the reduction requirement at the 5th centile treatment efficiency. The error bar on the total cost represents the 90% probability prediction uncertainty of the cost for meeting the watershed total phosphorus reduction using cover crops, filter strips, and wetlands simultaneously. This $2.7 to $9.8 million range is our best estimate of what it would cost to fix the total phosphorus problem. The broad range comes from the uncertainty in the lost opportunity from the price per bushel farmers receive from crop sales. The text within each stacked bar is the acreage of cover crops, filter strips, and wetlands that would have to be implemented. With this level spent on total phosphorus reduction would come between 46% and 100% of the total nitrogen reduction requirement, pending the realized efficiencies of these agricultural best management practices for total nitrogen treatment. So for context, we note that the drinking water treatment plant on Harsha Lake is currently spending about $700,000 annually on a granulated activated carbon contactor to keep the water it treats safe to drink. With this explanation for how we research the watershed nutrient reduction costs, I will hand it over to Matt to talk about the specific economic modeling associated with estimating the incentive the drinking water treatment plant on Harsha Lake might have to participate in source water protection.
Thanks, Chris. Waiting for my presentation to show up. Okay, so I'm going to talk about economic modeling of source water protection using the Bob McEwen Water Treatment Plant as a case study. We use the same watershed Chris just talked about, the East Fork watershed, with Harsha Lake as a source water for this treatment plant. In order to work through the steps James presented, we started with data from the Claremont County Water Resources Department, including operator logs, paper records, invoices, and electricity bills. We also have data from the U.S. Army Corps, including reservoir characteristics like pool elevation. We were able to compile 1,826 daily observations from January 1st, 2007 to December 31st, 2011 of real cost data and measurements from this treatment plant. The Bob McEwen Water Treatment Plant has a 19 million gallons per day production capacity, but on average during this time period it produced about 5 million gallons per day. It used conventional clarification, filtration, and chlorine disinfection, and during this time degraded water quality was associated with nutrient loadings from agricultural upstream. So following those general steps that James presented, we developed this more detailed framework for linking drinking water treatment costs to source water protection costs. It identifies the required data elements and time series analyses to develop the models required for estimating how watershed management and its associated costs result in treatment cost changes. The white boxes represent the source watershed side. Chris just talked about this right side, and how the SWAP model can be used to understand watershed management and estimate costs of land use change, in this case, the agricultural best management practices. The approaches used to model the water treatment side are in the shaded boxes. Based on the data we acquired from the county and the Army Corps, we present and discuss two time series modeling approaches and their application: error correction models, or ECMs, and polynomial distributed lag models, PDLs. The error correction model is used to develop a cost function for the drinking water treatment plant that is based on water quality variables measured in the raw water before treatment. The polynomial distributed lag model is used to translate estimates of watershed pollutant load reduction to the significant water quality variables at the plant. By estimating the cost savings at the plant from improved water quality and comparing it to the cost of land use changes, we can estimate the incentives the treatment plant has for protecting its source water. Most of the studies that James found in the literature review only estimate the treatment cost savings from improved source water quality. They did not take the extra step of estimating the cost of pollution control or land use change, which is needed for understanding the incentives. So we need time series analysis because we have daily data. We are interested in the long-run relationships for source water quality and cost to understand how they move together through time. Also, because drinking water treatment plants adjust treatment to accommodate episodic events, we want to examine short-run deviations from the long run. The error correction model allows us to do that. Changes in variables can have a long-run effect, a short-run effect, or both effects on treatment costs. We use cost per 1,000 gallons as our dependent variable. It is the daily aggregated chemical costs, pumping costs, and granulated activated carbon costs. On average, our cost per 1,000 gallons for this treatment plant was about 55 cents per day. Our cost function is made up of final production per day, raw water total organic carbon, which was a weekly measure that we had to convert to a daily observation using a step function, meaning the value remains constant over multiple days until a new measurement is taken. We have raw water turbidity, raw water pH, and pool elevation minus the Army Corps' guide curve, which is a target pool elevation depending on the season. For temperature of raw water, actual measurements of total organic carbon, spring and summer months, calendar years 2007 through 2010, and a process shutdown that occurred on April 15, 2011 that led to a spike in the cost per 1,000 gallons, we use categorical variables. Summary statistics and a graph of our total cost function can be found in the supplementary information at the end of these slides. From the error correction model, we learned that raw water total organic carbon did not affect treatment costs in the long run or short run. The drinking water operators did not change the treatment process based on total organic carbon unless there was a large measurement. So we focused on turbidity like many other studies in the literature review. For turbidity, there is both a short run and a long run effect. A 1% decrease in turbidity, which was about 0.11 NTUs, leads to an immediate decrease of 0.02% in treatment costs and another 0.1% decrease over future time for a total effect of 0.11%, or a turbidity elasticity of 0.11. It costs the drinking water treatment plant about $2,700 per day on average, or about $994,000 per year for chemical pumping and granulated activated carbon costs. So a 1% decrease in turbidity leads to about $1,120 per year decrease in those costs. So based on the error correction model, we know that turbidity is important for treatment cost. Our next step is to translate nutrient loads entering Lake Harsha to turbidity. We chose phosphorus load for a few reasons. First, total phosphorus has a strong affinity for soil and natural clay particles. Therefore, it has a link to turbidity. And it also has a link to producing algal blooms, which also increases turbidity. Finally, Chris showed that we can use the SWAP model to estimate changes in total phosphorus load using different agricultural best management practices. We chose the polynomial distributed lag model for a particular reason. We believe that a pound of total phosphorus can impact raw water turbidity for many weeks, so we need to take that into account. This particular model allows us to do that by testing how many weeks total phosphorus will affect turbidity. We estimated turbidity as a function of total phosphorus load, pool elevation minus the guide curve, categorical variables for spring months and calendar years 2009 and 2010. When a pound of total phosphorus enters Lake Harsha, we learned that it does not affect raw water turbidity in the first week, but it does affect turbidity between weeks 1 through 5. A 1% reduction of total phosphorus load, which is about 11 pounds reduced per day, will reduce turbidity at the intake by 0.15% over the long run. Using the $1,120 in costs avoided from reducing turbidity, a 1% reduction in total phosphorus load only leads to $168 annual reduction in treatment costs, which is not much. Using the SWAP model results, the cost to control total phosphorus using cover crops ranges between $3 and $27 per pound removed. Multiplying the 11 pounds of phosphorus reduced times 365 days times those costs leads to control costs between $12,000 and $106,000. The bottom line of this analysis is if the drinking water treatment plant were to pay $12,000 for cover crops, it would only save $168 in treatment costs, suggesting no incentive to protect its source water using those cover crops. So, in summary, based on what James found in the literature review, most studies do focus on turbidity as the important variable for treatment costs. Our framework provides decision support for understanding incentives, but we would like to test it with different drinking water treatment plants and processes. This will help make sure the framework is generalizable, so we're looking for a variety of treatment plants to study. Our case study revealed no incentive to reduce total phosphorus from entering the source water from 2007 to 2011. Other drinking water treatment plants that face different water quality problems or have different processes may have incentives, so we would like to continue testing this approach. One of our potential ideas to generate incentives is to aggregate the benefits of drinking water treatment plants, recreationists, and nearby homeowners, the other beneficiaries that James mentioned, from improved water quality, which may provide better incentives for protecting a particular source water. Of course, our case study had some limitations. The drinking water treatment plant overtreats the raw water to reduce potential risks and protect the public, but this can hide the impact of source water quality changes on treatment costs. Also, not having the right data can obscure the incentives. For example, we had to make some assumptions about those weekly measurements of raw water total organic carbon. We have a variety of future research directions. As Chris mentioned, harmful algal blooms have been increasing on Lake Harsha. We're collecting new data from the Bob McEwen water treatment plant because it changed its process in 2012. 2013 was the first full year the drinking water treatment plant's new granulated activated carbon building was online. So we're developing a new economic study from 2013 to 2016 to see if the incentives have changed with the greater reliance on granulated activated carbon. We also have new data on algal blooms for Lake Harsha that may provide additional variables in our treatment cost model. Finally, we only looked at total phosphorus, but some best management practices control both nitrogen and phosphorus. Including additional nutrients in the polynomial distributed lag or the translation model may also change the incentives, so we want to look at that as well. And let me finally just acknowledge the co-authors on the case study, including Eric Heiser and Tim Nyer, the operators at the Bob McEwen water treatment plant. Thank you.
Okay, thank you to all the presenters from ORD and all the presentations. I'm gonna pull up the end slide. Okay. Okay, so thanks again for everyone who was able to attend. We hope you can join us for our next webinar, which is water security resiliency. Water security and resiliency, excuse me. And registration information will be on EPA's webpage, which was on that first slide, and it'll be distributed soon.